All right. Thanks, everybody, for joining us for this tech talk today. We really appreciate it. My name is Leslie Denson. I work here at Ascend with Sheel, who I know you guys are anxiously waiting to hear from. Just wanted to say thanks so much for joining us today. We love talking about this particular topic. We love talking about intelligent orchestration and declarative data pipelines. And I have always really appreciated this particular presentation because it gives a really great overview. So um, again, thanks for joining us today. If you have any questions throughout the webinar, please feel free to throw those in the Q&A as Sheel's going through and giving his talk. I will, be calling those to ask at the end. If you have any issues with the webinar, also throw it in that Q&A section. I'll be happy to answer whatever I can there. And with that, we'll get started. So this is Sheel Choksi, Solutions Architect over here at Ascend.io, and I'll let him take it away.
Awesome. Thanks, Leslie. As Leslie mentioned, I'm a solutions architect here at Ascend, which basically translates to working with a whole variety of customers on their big data problems. And as we all know, big data is such a uh, fragmented world. That can mean anything from data analysts who are trying to work with a whole bunch of data that they've won in their warehouse to companies with large data engineering teams and trying to move well, these days, mind-boggling volumes of data through. And so what we're going to be focusing on today is, as the title says, this intelligent orchestration and the key to declarative data pipelines. So we're really going to cover two different topics. One, we'll spend a little bit of time as to what is really a declarative data pipeline and what does it trade off with compared to an imperative pipeline, and so that we can understand the trade-offs and the pros and cons there. And then we'll move on in deeper into declarative data pipelines and how they're enabled by having more intelligent orchestration layers, or really more smarts in the system at that level. So to get us started, we'll just start at the beginning here of what's going on with data pipelines. And when you're just kind of getting started with a data pipeline, at its highest level, you've got some data somewhere. Maybe it's some transactional data in a database, maybe it's interaction clickstream data coming through streams and queues and things like this. And in this gray box in the middle here, this is where we're really trying to build out our pipeline so that we can get to the end state of some downstream use cases, right? It might be uh, ML models, it might be queries for BI tools, it might be publishing it with warehouses so that we can query it. And these days the world is getting more complicated, right? People are productionalizing data in warehouses that needs to go back through a pipeline and get delivered somewhere else. ML models are creating predictive results that we might need to do more with. And so even outside of this more simpler diagram, there's just a bunch of data that we need to move from one place to another. And so the typical pipeline in there, it might start with some scheduler to say when to run that code, maybe more naively every day at 10 a.m. or maybe a little bit more smart is on some sort of event trigger. The code itself, which, is your actual business logic. And then these days we've got awesome compute and storage engines, a very common one being in this case Spark, and then pushing down to storage and cloud. And all of these pieces come together pretty quickly. The hello world of a data pipeline, if you will, that first time that you're expressing that business logic. And it's all looking pretty great until we start getting into the world of some more complexity. And where does this complexity start sneaking in? Well, at its most basic layer, you need to start dealing with the actual ingest and formatting of that data. These days data is spread in so many different locations. It might be APIs, it might be databases, it might be internally built systems. So you kind of have to finish that first part of it, of the ingest and the formatting. And then you get into the dependency tracking, right? Typically your pipeline is not just going to be that one snippet of code that we were just looking at. And so you just need to figure out, okay, from this step of code, what other code are we moving into? And then what code? And then of course, on the actual of the running that code and pushing it down into the compute, in this example with Spark, we need to optimize Spark. There's parameters that you have to feed in. The parameters that you use with some sample data set for development aren't necessarily going to scale that way in production, or even scale that way consistently in production, right? Differing data volumes each day. And then, of course, I hope, some amount of error handling so that you have some idea of when things are breaking and so that you can maintain it. But then the complexity just keeps increasing. And we start getting into more work that we need to do in this pipeline, where we want to start building out, for example, data profiles. If you wanted to build a report that is doing weekly aggregations of a data set, then you want to profile your new data that's coming in every day so that you understand which weekly aggregation that it might affect, which ties into this next box here of incremental processing, right? The more sophisticated that we want to get in the pipeline, the more that we need to build around it. And in a similar vein, right, in terms of optimizing these pipelines, making sure we're not just rerunning the entire data set all the time, we start getting into intermediate persistence, which is, as these jobs are running, they can create intermediate artifacts so that if things fail, if business logic changes, we can rely on uh, not having to restart the pipeline from the beginning, but instead restart from the intermediate persistence. And then that's sort of what ties into this data and job deduping, is with this intermediate persistence, leveraging it effectively, making sure that we're not just doing naive pipeline runs from the beginning, and properly leveraging it so that we're saving on computational costs, so that data is being delivered efficiently and quickly to where it needs to go. And if we weren't tired of enough complexity yet, once we start getting into these enterprise scale platforms where there's just a huge number of systems moving, we get into this advanced tier where now we need to start, because there's so much flying through the system, be absolutely sure that is the right data in the right place that got processed with the correct code. Are we positive about that? Are we positive that this artifact was generated with this code and not with some other code? And as we are working through that, as we're generating more artifacts and we're trying to keep track of which data and which code go together, um, what are we doing with the old artifacts and the garbage collection of it all, right? As we create a new artifact with a new code change, are we cleaning up the old artifact? This is not just important for the storage capacity and keeping things clean, but also for compliance reasons, right? As we get into a world of GDPR, CCPA, sensitive information redaction, are we positive that once we removed it, that we have removed the old artifacts and that we're in compliance? And then as we continue to get into enterprise systems and the larger and bigger platforms that we have here, we need to start getting into lineage as well, as we have so many developers working on things and so many different use cases. How do we know exactly where did this certain piece of data come from? What code transformed it? Is it the correct stuff? And to be able to walk through that lineage, to have that certainty of when you present some report, let's say in a BI use case, that we know exactly where that report came from. We know exactly where all of those columns came from, and that we know that it is correct. In a simple case, even like a public company trying to do revenue reporting, right? We need the lineage there to understand that it holds up to an audit, let's say. And then the fourth piece is the security and governance, right? Are people accessing the right sets of data? Are we making sure that people don't have access to more than they need to have? That they're accessing the right resources, so that they're accessing the ready-made data sets, for example, and not the raw ones, and all the governance that goes along with it. And then you kind of take a step back from that huge set of just red boxes that I just kind of went through, and even more that exist. And you kind of realize that 90% of the time and the pain of a data engineering pipeline, we're spending on stuff that's not actually the business logic and not the task that's at hand. And really, it's because there's just a lot of hidden and inherent complexity in a data pipeline. It really makes you kind of remember back to how we got started, where in the hello world, we just had some code and some business logic that we wanted to apply. So kind of with all of that context around data pipelines and what they look like, how do we get back to simplicity, right? How do we get back to this hello world where data engineers like ourselves can focus on business logic and creating impact for the business and not all of this inherent complexity? And so in order to do that, we kind of have to take a step back from the data engineering pipeline itself and answer some key questions, the foundational questions of what you end up having to answer every time you're trying to build a pipeline. Now, these questions might look a little simple, but the truth is that, you know, as you're building these pipelines, these are the things that are kind of just going through, right? Whereas when do I run my code, right? So I have a piece of code that does some business logic transformation. When do I need to run it? And so once you decide, okay, I'm going to run it this often, then as you get embrace some more of that complexity, it's then the next question is number two here is, did I already run this code on this data? Because then maybe I don't actually need to run it. Or in question number three, do you actually need to run it again? Because maybe the code has changed, or maybe the data has changed, which is questions 4 and 5. And then finally, you have to then basically recurse on question number 6, which is how was that data used downstream? And then figuring out all of these questions again of, okay, then do I need to run my code? Did the data change? Did the code change? What needs to be done? And the codifying part of these questions is really what we're seeing. And so when we take a step back again, it's easy to start thinking about like, wait, hold on. Where did this complexity come from? When we're looking at things like a database and a warehouse, you get to just write your query. You're not worrying about where things are stored. The governance and access is all handled. And that's because you have this database engine that goes through the middle here. And it's a non-trivial amount of code that you don't have to think about. And then all of a sudden you get your results. But in data engineering, when we're building these pipelines, we're really recreating this database engine in a lot of ways and self-creating thousands of lines of undifferentiated code to handle these same problems over and over again. And to put an even finer point of it, we have fantastic computation engines in the data engineering space now. You know, whether it's Spark or Storm or Kafka or whatever it is that we're trying to use. But we're essentially manually creating a query plan for every single stage of a pipeline and every single pipeline and the dependencies across all of that. So when we take a look at, you know, what is in the ecosystem today for us and building of these pipelines, you know, we can kind of look at some of this evolution of it, of from where we started. You know, the good old days of cron, let's say, or Airflow, where, you know, these are highly coded up orchestration engines where you're manually coding everything up on yourself, you're self-deploying, and figuring out exactly what to do at every step of the way. Then we kind of moved into 2.0 here with sassifying some of these orchestration engines, right? So removing some of the pain point around, you know, where is it being deployed to, you know, maybe adding a little bit of a GUI experience to make it more accessible to more people. Maybe some of the code is being templatized and auto-generated so that you're not mechanically building every repetitive step of the way. And this really helped increase the reach of who can help build pipelines and create them. But it still feels like there's something lacking here in 3.0 because the inherent complexity that we talked about, all of those boxes that you need to figure out, everything that tacked on top of Hello World is still unsolved. So it's starting to take a look as like, what can we do better, right? We've got some examples around the database engine. We've got some examples around other systems that handle this. And we started thinking about things like declarative programming models. And so for those of you coming in from the data engineering space from some other part of software engineering, right, this is a trend that we're seeing in other areas of the software engineering space where complexity is massively increasing. For example, front-end development. And front-end development used to be focused primarily on HTML, CSS, and smatterings of JavaScript. Now, you know, the vast majority of sites that have complexity and can do a lot more are becoming these single-page sites. And in response, what we see a great gravity towards in the market is React, right? Moving to this control declarative system in order to reduce the complexity that a developer has to deal with. And for those of you who are like front-end development, what, right? You see the same trend in the lower levels of the stack as well, right? Kubernetes for handling your app deployment and making sure that, you know, if you want these two pods running, they're just always going to be running. or Terraform or CloudFormation for infrastructure, right? Super complex set of rules to figure out, your deployment and your infrastructure and your subnets and security groups, let's say. But moving that into this declarative mindset that you just dictate, here's what I want for the security group, here are the permissions, go ahead and let a different system deal with that complexity. And so this started to become really compelling when applied to the data space. We're going to hop into that in a moment, but before we do, just two more definitions for folks on really what is declarative. So we'll go with the canonical academic definition here of declarative programming, where, and highlighted in red here, you'll see we express the logic of a computation without describing the control flow. And to put it even simpler, it's really just imperative is the how, where you say how to do something, whereas declarative is the what, like what should it be. And I'll use an example again outside of security groups and Terraform type deployments of something like React and in the front end, right? This helps us move from imperative to declarative on. Imperative was our jQuery days, right? Of add class to button once network request is going, so that button is disabled, right? And then in React, right, we flip that paradigm. We no longer say add this class at this case. We just say, hey, for button state, if the state includes loading, this class should be there. And the state management and React will true up and figure out how to add and remove that class as appropriate, right? So we're just simply saying when and what the class should be, whereas the how is all taken care of by a different system. And so if we apply that to what this looks like in the pipeline orchestration of it all, we can invert this paradigm where right now we have a scheduler that controls our code, right? The scheduler says, hey, based on some time or some event, go ahead and run all of this code that handles all of these boxes. We can instead lift up our code to the what layer, to the declarative layer, that then dictates what the scheduler side should do. And by switching these two, there's some profound implications here. The code is now actually declarative, which means it's not actually responsible for all of these incremental pieces like ingest and incremental processing and profiling. The code just says what it wants to have happen. The control plane, as we can call it now, because it's no longer just a naive scheduler, the control plane can handle all of the what to true up everything that the declarative layer has said. To make an example on a data pipeline, let's say we have a very, very simple pipeline that at every 10 a.m. is just grabbing some new data out of S3 and copying it to a Redshift, let's say. That is the imperative format of a pipeline right there. And the declarative version of that is like, hey, everything that is in this S3 bucket should be in this Redshift table. I don't want to have to figure out how to figure out what is the new data in S3. I don't want to have to figure out when to run. I don't want to have to figure out any of that. What I want is to declaratively say everything in this bucket should be in this Redshift table. And then the control plane can figure out everything that needs to happen in order to true that state up. So hopefully now at this point, we're all feeling quite comfortable as to what an imperative type of system is versus declarative and how that looks in data pipelines in particular. But with all things in software, there's always trade-offs in different models. So let's briefly work through some of the pros and cons of an imperative model versus a declarative model. And this will be specific to data engineering pipelines, obviously, but in an imperative system, it's highly flexible because you can code up anything that you want to do in any level of basically list of instructions of how to carry it out. And that's what gives you that high level of control. But with imperative systems, what we often like to joke internally here at Ascend, you have the ability to do anything and the responsibility to do everything. And so you have to handle your own state management. you have to handle all the code that deals with all the assumptions of what's going on with what data and where it's moving. You have to manually optimize. If there's an opportunity to reuse an already created artifact, if there's an opportunity to create something that's incremental that's not currently being incrementally done, you must manually optimize all of that. You need to figure out your own integrity checks and figure out what's the current state of the system. And if you naively scheduled something to run every day, and for some days it broke, you need to figure out what state am I in, and which partitions do I need to repair, which ties into this failure management as well. So those are the cons of an imperative system. But let's compare that to declarative. So in declarative, you have the benefits of typically what we're seeing is 90% less code that you're writing because of the vast majority of the code. Again, the code doesn't disappear. It's the code that you're responsible for, right? The code gets pushed into this control plane or this query. Oh, sorry about that. I think my headphones disconnected there. But the code that you're responsible for is now being pushed into this control plane, which allows you to do things like faster development cycles and faster ability to adapt to change because you are just working at the declarative business logic layer and not at the imperative how to do it. And less maintenance, right? Things like repairing from failure state are no different than an everyday system because it's always just going to be the control plane managing and figuring out what needs to be done to correct. However, because we said everything has trade-offs, there's cons, of course, to declarative. And the two main cons that you'll see in a declarative system are, one, because the declarative system is wired up in a certain way in order to take, in a case where we were saying we just want to always mirror up everything in this blob store to Redshift, then any type of behavior overrides are typically done with annotations. And then the second part, which is what we're really going to get into, and this is the link from the first part of like what is declarative and imperative to what is absolutely necessary as part of declarative pipelines is a domain-specific control system. The control system has to intimately understand everything that's happening from the declarative logic and what's happening in the system in order to figure out what to do next. So in the example of React again, right? React is constantly evaluating state and constantly evaluating its virtual DOM, which it trues up with actual DOM to figure out what needs to be done and what manipulations need to happen, right? And that wouldn't be possible if React did not totally understand everything that's going on within the world of browsers and DOM and keeping track of all of that state. So similarly, in a declarative data engineering pipeline, you need something domain specific, specific for data that can properly react to the changes in the system and figure out how to translate the request from the declarative what needs to be done to the imperative how to do it. And so really what we'll segue now into is what a control system can look like for declarative pipelines, and even more specifically, the one that we've built at Ascent. And so how did we really get there? Well, like all good engineers, right? We started from what are really the requirements here? And what could really be handled by a good control system that is non-differentiated and doesn't actually need to be specific to any one particular business use case? And it turns out there's quite a few things. Even outside of some of that inherent complexity that we talked about earlier, there's so many more things that match into what a control system looks like for pipelines that can be handled here. I'm not going to read them all out to you all, but you should be able to take a look at these and see a bunch of these that resonate in terms of code that all of us have likely probably built at some point or another as part of trying to make these pipelines work. And so what can we really do about that, right? What can we really do is take all of that, combine it into that control plane that we talked about in terms of evolving that orchestration paradigm, and really simplify that into four main groups that they all kind of tie into. We're going to dig into each one of these concepts as to data-aware, autonomous, scalable, and self-optimizing. But given these 4 key concepts, the control plane can handle those variety of issues that we just talked about. And again, brings your code up as data engineers building at the declarative level. Almost really the hello world example again, where you're just focusing on the business logic. And so we'll use the sense control plane as the example here. And another way to think about this is a 3-tier system where you have a logic plane at the top. This is the what needs to be done. This data set needs to be replicated over here, or this data set needs to be aggregated and then sent over to this other place. That's the what layer of this top level logic plane. Then in the middle, you have this new control plane that we've been introducing that handles the translation of the declarative code of what do I want to have happen into the how does it need to happen. The, oh, I see, the S3 directory is almost nearly mirrored to Redshift, but there's one new file that hasn't been dealt with yet. So let's go deal with that one new file. And then let's execute a job to do that. And that's where we tie into the execution plane, the actual work that needs to have happen. Again, we're using Spark as an example here. And so the actual Spark job to go deal with that one new file, incrementally process it, and add it into Redshift where it needs to be so that the control plane is satisfied and knows that everything is done per the request of the logic plane. And so in order for the control plane to do and create the how, these are the 4 kind of key concepts that we were just alluding to. And so the first one here is being data aware. This is really the domain specific part of the control plane, right? Rather than just trying to say, hey, run this arbitrary Python script or run this task at this time. It needs to actually know all about the data. Like, where's the data? Where's all the data laid out? Where's all the code? What went where? And with a deep understanding of all of that, then the control plane can actually be autonomous, which is the second part here, and figuring out, what needs to actually happen given its understanding of all the data, where it all is, what actually needs to happen in order to do the right thing and keep the what in sync. Now, of course, none of this would matter if the control plane wasn't scalable, right? And so in big data, we're dealing with easily trillions of records, billions of different partitions of data. And so the control plane not only needs to be able to keep track of all of the actual data and where it's going, but also all the metadata in order for it to react quickly, right? React in seconds to changes that happen in the system, what needs to happen next. And then the fourth part here, right, which is the huge benefit of moving to this declarative construct is that it can do automated optimization far beyond what we can create in manual hand-coded optimizations, right? It's like, these days, right? Everyone's like, you don't beat the C compiler, right? You're not going to beat the compiler, right? Let the compiler do the optimizations that you possibly can to hand construe, and you focus on your code. Not like the old days, right, where it was like, oh, I'm going to hand unroll this for loop or anything like that. And so same thing here in the data engineering control plane, right? What are the optimizations that we can do that massively allow an automated scale to create as opposed to us manually trying to do it? And so given these 4 must-haves of into the control plane, how did we actually build this at Ascend? And what are we doing under the hood? So we'll go into each one of these sections for a bit. And the first one is being data aware. And this, again, being specific to the domain of data engineering pipelines. And the one way to think of data aware is literally track everything. If anything is happening in the system, data flying around, metadata, Spark jobs completing, not completing, track it, all of it. And so what does that look like for us at Ascend? Of course, there's the more basic component level understanding of what's in the system. The component might be a certain code to transform. It might be a connector to go get data from a certain warehouse or a certain blob store. And then under those components, you get to the fragments. And the fragments are where things really start getting interesting in this second layer of the control plane, where not only can we start tracking the location or the output of any particular job that's happened, and the data SHA, right? For those of you not familiar with SHAs, right, they're just a fingerprint, essentially, a way to take a huge set of data, combine it into something compact, and know, with some cryptographic or algorithmic certainty that it's a representation of exactly what's in there. But those two parts are easy, right? The location of where the artifacts are produced in the data SHA. Where we start getting a little bit more interesting is in the data profile. So in that artifact that was produced for that fragment, what's the schema of it? What's the min and max of the different fields that are happening? What's the lineage of it? So where did it come from? And with all of these pieces, we're able to, start doing things like answering questions of like, did data come in late from when it was supposed to, right? That can come from the min and max of the fields. So starting to understand not just the SHA of the data, but the profile of the data, as well as the job that was used to produce that fragment, right? Was it on a Spark engine? Was it on a different engine? What input fragments were used to create that output fragment? What code was used as part of that job? And of course, as you can imagine, we SHA that too. And how long did it take? How many resources did it use? All this kind of meta information that we can use as part of the control plane to figure out how to execute the next job or what next job needs to be done. And the third one that we'll talk about here is a concept of a PSHA, or you can think of it as a fingerprint for one particular partition. And we're going to spend some more time on this one, but this is really a big concept into knowing what's there. The PSHA helps us understand what is there and what created it. And the really cool part about the control plane is where it sits in here is it's in the perfect place to see and record everything that's flowing through the system. Because it's the one that's creating and executing all of these jobs, it can understand what's happening and where all the data is moving. But it also has the ability to act on it. So not just record everything, but then figure out how to act on it and decide what to do next. And that's really the second part here, where we talked about being autonomous is to respond and adapt to the changes in the system. So we're going to go really deep now technically here of like what we talk about in terms of how the system is able to understand the change that's happening and what needs to happen next. So really the way to think about a PSHA is for input data where the system starts, it can just be the data SHA itself. Whereas for any transformation, it's a recursive SHA of the component's own definition plus the SHAs of all upstream input fragments, which lets us actually very quickly determine, is the PSHA different than what we would have expected it to be? Right? There's a PSHA of what we want the system state to be in, and then there's the PSHA of what was actually created. There's just a very set of simple rules that we could go through for the PSHAs, but essentially at any given point in time, you could know, hey, this little piece of data over here is out of date. And there's all sorts of cool things that we can go into. Happy to in the Q&A section of, how do you know the inputs? How do you know the PSHAs? And really what this comes from for us is for something like data profile or SQL of being able to parse and analyze it, being able to use that data profile, being able to understand for a certain input fragments for a certain fragment, I should say, what are the input fragments that feed into it. And so as we think about the system of what needs to happen is it's just constantly evaluating. It's constantly looking at these PSHAs and figuring out, are any PSHAs out of date for what they need to be? And this turns out to be quite a simple yet elegant concept that we can apply to all the different kind of components. From for when we're first ingesting, is there new sets of data? Okay, great. Let's go ahead and create that as a new fragment. There's a new PSHA there. And for a transform, there's a new PSHA. So which downstream fragments does that affect? And go ahead and run and create the Spark job to fix that. If we have something like a code change, then that means the p-SHA for that whole component has changed. And so we already know all of those input fragments are invalidated, and so you get an autonomous backfill of historical data changed with that code change. And again, a simple set of rules for, if a new fragment has appeared, if a fragment has been updated, or if a fragment gets deleted. Now, we're going to kind of take a step back up and remember to the key questions, right, of everything that we needed to codify in order to build a data engineering pipeline, which is first, when do I run my code? All the time. The control plane is running all the time to figure out, are there any p-SHAs in a mismatched state? And is there any work that needs to be done to quote unquote fix and repair that state? The next set of questions, did you already run this code on this data? Do I need to run it again? Which data change? You can just check the p-SHAs to know what's in a state of mismatch and needs to be repaired. And then the last part of what's being used downstream, that's done through traversing the graph, traversing those p-SHAs, and determining which fragments are changed accordingly. And so we'll talk a little bit about, now that we talked about, what an intelligent control plane looks like and how it enables these declarative pipelines, we'll just go a little bit deeper into, how do we do this as scalable? And the first part here is we need to be able to detect changes efficiently. We need to be able to know um, what's changed and why without having to recompute all the p-SHAs all the time, which is actually kind of a very tedious process here. And so one of the ways that we do this is by creating more SHAs. So in the case of being able to leverage time series data of, for example, in this component A and this downstream component B, if we can see here that the partition over here has a dependency on this partition over here, and yet nothing in the whole 2019 tree has changed, we can actually create p-SHAs at every level of that time series hierarchical data and quickly evaluate them at every level of the tree. Get huge efficiencies here, obviously, of trees over lists, as well as the ability to um, handle multiple levels of SHAs and do SHAs across multiple different dimensions. And so this allows us to not so naively just compare every single partition SHA across all like billions of partitions, but do it much, much more intelligently. Another thing that we can do here is to keep the work streams tighter. And by that, we don't need to necessarily run everything, like if there's a big set of data, as one big Spark job. And so we can break that down into per partition jobs so that we can scale more effectively without all the typical problems of scaling Spark jobs, executor out of memories and things like big historical backfills. Instead, run it as lots of small partition jobs. Similarly, keeping caching of that intermediate data and being able to reference it so that we don't need to rerun something that's already run. And so we're going to focus on, we're going to skip this one. This one is a kind of a fun one, but we're going to skip this one today as to how we can tighten up some of the jobs and the processes. But the key takeaway is obviously with cloud scaling, there's a huge amount of different scaling costs, whether it's bringing up a cluster versus bringing up a VM versus bringing up a Spark cluster versus bringing up a Spark job. And so one of the things that the control plane can do, and this is, again, optimization far beyond manual optimization, is reuse Spark clusters when appropriate. Reuse VMs by packing more Spark clusters onto when we can, right? Everything that the control plane can figure out, and we have it here in the 3 R's of the reduce, reuse, and the recycle of it all. And another example of this is being able to use intelligent persistence in order to figure out um, what data already exists and figure out what actually can be reused or what needs to be created and where. And so in this, there's 4 constraints really that if you can play by, then you can leverage a lot more out of your storage layer. And so these 4 constraints are fragments need to be immutable. So only write to them and do not update them. and so generate them as completely separate artifacts or fragments. If you can have idempotent transforms, or idempotent fragments, I should say. So given the same inputs and the same transforms, you will always get to the same output. Then there's huge predictability in the system where you can reuse an artifact of data because you already know what is being inputted to it. The third constraint here is that if we can do committing of the data set by metadata mapping, so because we're writing all the fragments to a new location, every fragment creates a new location, instead of trying to update the same place, we need to be able to commit by just saying, hey, this data set is now available over here, or to the fragment or partition level, part of this data set is available over there. And then the last piece is be able to do that garbage collection and cleanup, because abandoned data that is no longer actually relevant and nobody's pointing to it does need to be cleaned up. And so if we can solve for all four of these things, you get huge benefits from it. And so part of that is using metadata to be able to point to the same fragment level without having to recompute anything, because the PSHAs give you this guarantee. As well as the ability to, while processing new data sets, still surface old results, because that's what's being pointed to from the previous runs and the previous PSHAs until the new data set is ready. So atomic lists and reads and writes and all the stuff that you would hope for. Again, complexity that you would have to self-build in pipelines that a control plane or this engine in the middle can take care of for you. And so what it looks like in a Ascend's world is at the fragment level, the bucket points to a UUID that represents that data set with the right data profile job and PSHA that we're storing in the fragment, but it gives us these specific abilities. For example, if I were to copy one pipeline and move it to a different place, because all of that is then still referencing the same PSHA, it's a zero cost operation, both in terms of compute and storage. We can data deduplicate as we're developing from staging to production, right? We can almost do like blue-green deploys, if you will, where we pre-process all the data in staging that we will need for production. And when we deploy to production, we see that all of those PSHAs already we have the output fragments. So we're just simply adding a reference for the production components to that existing data set. We can even do things like rollback and restart as long as we're still in that garbage collect window. We can kill a pipeline in the middle and restart from exactly there because we're only fixing the PSHAs that are mismatched. We can roll back to a previous code definition, which will create the old PSHAs again. And that'll just simply point back to those previous artifacts that we have in the bucket. So you get a zero downtime revert. And so really what this is all pointing back to is we can do things faster and cheaper than we would when we manually optimize. And this is just one example at the persistence layer. And so winding all the way back up as we wind out and close out today's talk and recap here a little bit, what did we really talk about is that we spend a huge amount of time codifying and preparing for, these key questions of a data engineering pipeline. When do I run my code? Did we already run it? Run it again? What data changed? What code changed? And just recurse and redo all of that codifying again and again. And by having something that's data aware, by just tracking everything that's going on in the system, you're able to build something that is essentially a control plane that's constantly evaluating and repairing, figuring out what work needs to be done if it's not already done, and taking care of answering, and not only answering, but then also dealing with the code to build for all 6 of those questions. And the trick is to do it efficiently, to be able to do this at scale, and be able to handle all of that with also leveraging metadata and creating optimizations far beyond what we could manually create. And if nothing else, It's all because of these PSHAs, like this ability of being able to create these fingerprints and being able to recursively create these fingerprints gives us that ability to know what's in the right state, what's in the wrong state, and go ahead and create the right job to fix it. So that's what we do at Ascend. We create declarative pipelines where data engineers are empowered to do a lot more faster, work more effectively with less code. And if you are curious to check out more of that, a lot of ways to get in contact with us. Please feel free to schedule a demo, join us in Slack and ask questions or trial or email me um, and love to talk more about this kind of stuff. But really appreciate you all taking the time to listen today. Hopefully that was interesting in getting a sense of a different way of thinking of paradigm for data engineering pipelines. And please do let me know if you have any questions.
Yeah, so as I'll echo what Sheel said, thanks you guys so much for joining us today. We do have a couple questions that people threw in during the talk, but don't forget if there's anything that you want to ask, please feel free to throw it in the Q&A. So Sheel, I think the first one we got, if I'm reading these in the right order, is there a pipeline or is there a data set that is better suited for something that is imperative? I mean, obviously, and I'll say this, we've talked about the declarative versus imperative, but I think they're looking to see if that's kind of always the answer, or if there are ways where, maybe imperative is the way to go.
And so I think it's that's an interesting question, and I think it's basically where the flexibility that's required might push out of what a declarative control plane is already ready to do. And I think the reason why this question is tricky is because similar to database engines, control planes, right? They're always trying to handle more and more use cases. And so they're always going to get more and more compelling, right? Some SQL query that you had to manually optimize 10 years ago is now probably already optimized by the query planner today. And so the way I would think about it is not necessarily from a like this use case versus that use case, but more, is the use case doing something that is so far out of what where the control plane can handle today that you need to drop into the imperative layer to hand customize and hand code that in, and then immediately looking for opportunities for what is the declarative construct to replace that, right? Like how is the way to say that declaratively so that you don't need to do it again. And so I'm trying to think of some ad hoc examples. Some ad hoc examples are side effect based things, right? We talked about how the transforms should be idempotent, right? And they should be given certain input data sets, given that certain transform, you want to always be able to create that same output, right? That's a key tenet here. And so if we start thinking about things that have side effects in that system that cannot be pushed down to the declarative control plane, then that would be something that you would want to push into the imperative on the highly flexible.
Okay. Next question we had is, what kind of resources, just from an infrastructure standpoint, does this take? And maybe I know, and you talked a little bit about reusable Spark jobs helping things, this, that, and the other, but from the difference between imperative to declarative, what does the resource requirement look like?
Yeah, absolutely. It's a great question. I assume, and if I'm misunderstanding it, please do clarify. But what I assume we're talking about here is that, previously, if you just had, let's say, a scheduler, and then you just had your compute engine, that's all that was there. So you just deployed your scheduler, you deployed your compute engine. Great, no other infrastructure, but you hand coded everything else. In this paradigm, since we are deploying a control plane, there's extra infrastructure for the control plane to do its business, right? And so what it looks like for Ascend is because we run on all three clouds, we deploy a Kubernetes cluster that has a series of microservices that are basically doing all of this work. So work to do basically grabbing profile of data from the columns, work to manage the Spark clusters and keep track of how long they're running and what resources they used. Other services that just well the actual thing that's constantly evaluating PSHAs, we call that our scheduler, and figuring out what's out of state and what's broken. And so, what we're really talking about is, some Kubernetes for some more infrastructure there, and then a metadata store. And so, going to an object store to figure out all of these PSHAs and mismatches and whatnot, or trying to go to the actual data, would be quite slow. And so we actually want to store all of that metadata into a meta store. And in our case, we use a database in order to do that. And not in maybe a conventional sense of your typical records, but in a sense of storing these trees and everything that we talked about in order to help quickly figure out what's going there. And then, of course, a lot of that is backed in memory store as well to do this very, very quickly.
And then I think the last question that we have, unless anybody else, like I said, feel free to pop them in, is if folks want to make that jump from imperative to declarative, what are some challenges that they might face? Like, what are some of the kind of hidden roadblocks that maybe people need to think about when making that move?
Yeah, it's a great question, and one that I've been through a couple of times. As if you were wondering why there were so many front end examples, is I've spent quite a few amount of my time in my career in front end, and the the jump from imperative to declarative can be a bit of a mental jump. The vast of creation of code, when you're writing it procedurally or object oriented or whatever, and you're creating code, most of the time you're dictating commands, right? You're creating very imperative statements, and so that first time you jump into declarative can be sort of like a wait. Like what I want to say is I want to say, take this file and put it over there. And that's maybe the construct that you're used to. And so the jump there, the obstacle can sometimes be, okay, wait, hold on, take a step back. It's not about just take this one file and copy it over here. It's what is really my problem space. It's really that I want these sets of files to always be materialized in this warehouse. And sometimes that can be, thinking at a higher level. Sometimes that could be thinking about the problem a little bit differently. And that does take a little bit of getting used to. So whether that's, jumping from plain JavaScript to a framework like React, or whether that's in these data engineering pipelines, coming from that imperative world to something like Ascend, there can be a little bit of ramp up time there, but something that we have, or something that I spend a lot of time doing with customers and helping to work through the pipelines that they're thinking of, and what it looks like in a declarative framework.
Okay, awesome. Well, I think that's all that we have today. So Sheel, thank you so much. We appreciate it. And I'll say for everybody out there, if you're interested in learning a little bit more about the Ascend platform, obviously you can reach out to us. We'll be sending these slides out and also a recording of the webinar as well. So you can watch it on demand if you'd like. But we do have a kind of roadmap sneak peek tech talk / webinar happening next week. If you go to ascend.io, the registration link is right there on the front if you are interested in seeing what we have coming up from a feature standpoint. But really appreciate you guys joining us today and attending. So thank you again.
Thanks, everyone.